You can use the NVIDIA DDS texture tools for Adobe Photoshop to read and write cube maps, such as environment maps or reflection probes. This plugin can import unfolded cube maps, such as in this forest here. These must have an exactly 4:3 aspect ratio. Alternatively, you can save cube maps in linear format, which is in the format you'll see when you import a cube map from a DDS file. These images must have an exactly 6:1 aspect ratio, and have their faces in the OpenGL cube map face order of +x, -x, +y, -y, +z, and -z, or in terms of directions, right, left, up, down, forward, and backward. Select File, Save As, and then choose DDS NVIDIA Texture Tools Exporter. Once you've seen the plugin, click on Texture Type and then choose Cube Map.
Hello, everyone. Welcome back. I hope you all had a great weekend. So today we are shifting gears a bit. In fact, in some respects, I think you could say we are going back to the beginning of the class, where the discussion is going to be on linear models. One of the reasons that we're doing this, perhaps the most important reason that we're doing this, is that this starts us down the path in looking a little bit more closely and a little bit more deeply at neural networks. Although for at least today, we won't be dealing with anything that we would call a neural net, at least not directly. Anyway, but to sort of recap where we've been so far, at the beginning of the semester, we looked at two methods, Winnow 2 and naive Bayes. And in both cases, I made the comment that these were linear models, linear classifiers. We're going to look a little bit more closely at this. And today in particular, we're going to go back and revisit naive Bayes, and I'm actually going to show you what makes that a linear classifier. But to get us started with this, let's start by looking at Winnow 2 again, where you'll recall that what we did was we defined a function that for now I'm just going to denote g of x. And that was defined as a weighted combination of the inputs. So simply multiply weight times input, add them up. And then what we did was that we tested to see if that sum exceeded some threshold theta. Okay, well, one of the things that I want you to notice here is that we could rearrange our terms a little bit and rewrite this like that. Notice it's still a linear model, and all we've done is shift the threshold. And you may recall that one of the issues that you had to deal with when you were learning Winnow was tuning that threshold theta. Well, what we're going to see before this unit is done is that you actually don't have to tune theta. You can learn it directly. And one of the observations that we're going to make is that this theta is really just another weight. that we can denote W0. And if we were to imagine that we were multiplying that times some fixed input of either +1 or -1, then we can rewrite this function like this. And this is a very common form that we find for linear functions. All right, another term that you'll sometimes see tossed about when looking at these models, we sometimes call them linear discriminants. Because what we are doing with these models is discriminating between, in this case, two classes, a positive class and a negative class. All right. Any questions about that so far? Okay, well, let's move on and let's take a closer look at naive Bayes. So the way we're going to approach this is we're going to recall that we had put naive Bayes in the context of Bayes decision theory. Where when we were done, we had defined a decision rule that acted as a discriminant. In other words, a classifier. It was discriminating, or it was classifying a data point in one of course, what we found was it wasn't restricted to two classes, but one of K classes. Well, for now, let's limit the discussion again to only two classes. And at the end, we can talk about whether or not we can generalize the idea to more than two classes. But you'll recall that the way Bayes decision theory worked was basically saying we were comparing the probability of a class, and we can go ahead and say that the class variable is equal to 1, given our vector of attributes. And in particular, we were testing to see if that probability was greater than the probability that the class variable is equal to 0, given that same vector of attributes. So that was the mathematical goal that we were working with. And what we found was that you could actually reduce this down using the naive Bayes assumption to look something like this. I guess I should have used D instead of N. If you feel more comfortable using D, go for it. Now, all I'm doing is I'm substituting into the inequality above. And we get this inequality instead. All right, I'm running out of room on the whiteboard. So before I erase it, let me pause and see if there are any questions. In particular, I want to make sure that none of this is new or mysterious to you. Okay, well, to give you a heads up of what I'm going to do next before I erase the whiteboard and move to the next page, I'm actually going to take the right-hand side of that inequality and I'm going to divide by that value on both sides. And so that's going to give me a ratio. So let's go ahead and do that.
New page.
When we do that, what we get is a decision rule that looks like this. Okay, and the first thing to notice here is that 1 on the right side of the inequality, you can almost think of like the threshold that we saw earlier with the Winnow algorithm. Except on the surface, looking at that ratio, that sure doesn't look very linear because we've got all kinds of multiplications and all kinds of divisions going on. But what we're going to do here is we're going to apply a little trick where we're going to take the log. And once we have done that, and I'm going to do this in 2 steps, we find it converts to this. And notice now that our threshold, because we've taken the log of 1, has now become 0, which looks even more like what we saw with the Winnow algorithm previously. And I was able to do this because when you take the log of a ratio, that's simply equal to the difference of the logs of the numerator and denominator. Well, we can continue this idea because now notice what we're doing is we're taking the log of a product. And if you take the log of a product, that reduces to a sum of logs. So I'm actually going to go ahead and regroup terms while I'm doing this so that I can simplify the notation a little bit. But this turns into I'll go ahead and block that off. Plus this sum again comparing to 0. All right, so what's interesting here is that we can take this and that becomes our W0. And then notice this is a sum, which is basically also linear. And so what we've done is we've reduced that ugly ratio of products up at the top down into a linear expression that actually is a linear discriminant. And what I'm going to do next is we're going to kind of push this a little bit further by talking briefly about an example where this example is often used as kind of the standard problem that enables you to demonstrate whether your model is able to learn, well, whether your model is a linear model or not. Before I do that, let me see if there are any questions. All right, so let's talk about sort of this quintessential problem. In fact, I'm pretty sure I've even brought it up previously in this class. That problem is the exclusive OR problem. Why is it doing that today? Where if we have two variables, x1, x2, and this represents the function exclusive OR, then the truth table looks like this. All right. And if we were to plot this in 2 dimensions, what we get is something that looks like this, where we have a point here, a point here, point here, a point here. And if I fill in these points, what they do is they reflect the points from the truth table that are in the positive class, where the open circles are in the negative class. Now, looking at that very carefully, I would challenge you to draw a single line, one and only one line, that separates the filled circles from the open circles. You'll find you cannot do it. And that's because exclusive OR is not linearly separable. Now, what's rather interesting is if we take this particular problem, and let's just suppose that those 4 examples define our entire data set. And what we want to do is learn a naive Bayes model using those 4 examples. What you will find is that it doesn't matter which of those vectors you use. If I want to know the probability of x1, x2, I'm sorry, wrong. If I want to know the probability of the class given x1, x2, I don't care what values you plug in for x1 and x2, and I don't care which class you look at, you're going to find that that probability in every case, unnormalized, remember that we're dealing with the unnormalized posterior. Well, I think in this case it may not matter. is that. In other words, we cannot differentiate any of the examples using naive Bayes in this case, because we have no way of saying which is the maximum probability class. They're all equal. All right. Any questions before I move on? The next step is to actually show you a trick that will allow you to get around this. Okay, not seeing any.
New page.
Within the world of so-called linear regression, and I know I just tossed something else in the middle because our topic of conversation today is actually classification. But linear regression, where you're trying to learn some function of this form, is what do you do if you know that didn't come up right. There we go. What do you do if you know that there is a nonlinear relationship in the data? Well, often what gets done here, and by the way, this is still classified as linear regression, is we introduce higher order terms. One of the classic, quote unquote, simple extensions is to create quadratic terms. And we can apply exactly the same idea with linear discriminants, where we just insert these higher order terms. So as an example, let's go back to exclusive OR. And suppose, now remember, I'm trying to define a linear discriminant. Suppose I define a new term. Let's just call it Z. And we're going to let Z equal x1 and x2. By the way, we can generalize this to real valued by letting Z equal x1 times x2. Because you can actually show multiplication and logical and are more or less the same operator, except one is in a binary Boolean space and the other one's in a real valued space. If we do that, our new discriminant function, still a linear function, looks something like this. Notice all I did was add a new term to the equation here, corresponding to the quadratic term. But I'm still learning weights that are related in a linear fashion to each of these terms in the equation. And what's interesting about this is that if we let W0, and by the way, there are many solutions to this equation. I'm just giving you one that I know works. Let's let W0 equal negative 0.1. Well, that didn't show up. Why didn't that show up? We'll let W1 equal 0.2, W2 equals 0.2, and W3 equal negative 1. Okay? Now, remember, this is our truth table. And we're going to be comparing this to a threshold of 0 by assuming that we've actually pulled that threshold into the W0 term. And then when we look at x1, and x2, and this is the table we're going to use. Now we can just plug in the numbers and notice that for the first one, that's just negative 0.1 because the other three terms drop out. And then, let's see, we've got negative 0.1 plus 0.2, which is plus 0.1. That's because the W1, X1 term drops out since X1 is equal to 0. Z also drops out because the AND would equal 0. This one is also hold on. Whoops, did I goof? I may have goofed. 0.4 compared to 0.5. Give me just a second. I think I calculated some of these weights wrong. Oh, that's the wrong spreadsheet. Well, X1 and X2 is going to be 0 because it's the AND. So I don't know how you're getting 0, 1, 1. Because you have to have both of them equal to 1 for the AND to be 1. Oh, no, this is right. Gee, never mind. This is correct. And I'll explain what I'm looking at, why I thought it was wrong in a second. So going back, just to make sure we're all on the same page, the weights are correct. So the W0 holds regardless. X1 is 0, so 0 times W1 is still 0. However, X2 is equal to 1 times W2 is 0.2, minus 1 plus 0.2 is plus 0.1. And then the AND is 0, so that drops out. And it's symmetric. That applies for both of those inner vectors. Okay. I don't know what threw me off. Now let's look at the last row where because of the X1 and X2 and the AND all being 1s, we're basically adding together all 4 of those terms. So we have 0.4 minus 0.1, which is 0.3 minus 1, which is negative 0.7. Okay, this is right. Remember, our threshold is 0. Because our threshold is 0, that goes to 0, that goes to 1, that goes to 1, and that goes to 0. It helps if I'm showing you what I'm looking at. Sorry about that. And that is the exclusive OR function. So by inserting that higher order term, and I just lost all you guys. Where'd you go? There we are. Hopefully you can see the whiteboard now. I had the wrong page up. Can you see it? Yeah, okay. So the red on the right is showing, in fact, the exclusive OR function. The higher order term did provide a way for us to separate the two classes. And when you think about it geometrically, this makes some sense because what we've done is we've now gone into 3 dimensions. Where we still have these, but then we have this up here. And I just reversed the positive and negative classes, but hopefully you can still see from that I'm able to separate the 0, 0, and 1, 1 points from the 0, 1, and 1, 0 points. What we've done is effectively take it into a higher dimensional space. This idea we're going to see later in terms of, you recall from the non-parametric discussion, where we were talking about kernels. And the idea that what a kernel does is it actually projects into a higher dimensional space. Again, we'll talk about that a whole lot more later. All right, so let me pause there and see if there are any questions. Or I also want to make sure that the whiteboard here stays up long enough so that when you go back and view the video, it just doesn't disappear from you, although you can always pause. Okay. So moving forward, there's a little bit of a preview. Some of the topics that we're going to be discussing include something called logistic regression, which is yet another linear model. But what logistic regression will do is it will sort of bridge the gap between the type of model that you saw in Winnow and the type of model you saw in naive Bayes, in that we will be able to interpret the results of logistic regression probabilistically, even though it looks a lot like just the weighted sum like we've been dealing with. And then we're going to look at a couple neural nets. The first one we'll consider is the perceptron, which is a very old model that was actually proposed as an attempt to model the way the retina in the eye worked. But as we'll see, it is also a linear model. And then a very, very similar model is called Adeline, which stands for adaptive linear network, or some will say adaptive linear neuron, because the network could be reduced to just a single neuron. And then finally, we're going to look at the support vector machine. Which, even though it too is a linear model, is perhaps the most complex of all of the ones that we will have seen up to that point. And out of all of these models, these four, well, actually, let's say all six, throw in Winnow and naive Bayes as well. The most popular algorithms are naive Bayes, logistic regression, and the support vector machine. But what is rather intriguing about all of those three is that the support vector machine has gotten a ton of attention because it has a nice natural way to incorporate these kernels. And once you've done that, we end up finding that support vector machines are no longer limited to linearly separable concepts, at least in the original dimensions. Okay, I do have another topic I want to move on to before I get into any of these algorithms. Before I do that, again, since I have to erase the board, let me see if there are any questions. Okay.
New page.
All right. So again, I want to step back and look at an issue that all of you faced on the very first programming assignment, and take a little bit of a closer look at what's going on there. And we're going to do this by considering the geometry of these linear classifiers. So let's begin by considering the two-class problem. And what we can do is we can sort of look ahead to where I'm heading with this, where we were dealing with more than two classes. And you'll recall that what you had to do in the multi-class case was define or to learn a at least in the Winnow example, learn a separate model for each class. So let's do that. Let's suppose that we are going to define this function g of x, that's our discriminant, by comparing two different discriminants, g1 and g2. And we can take the difference just like we did when we were looking at naive Bayes, because what that will allow us to do is then compare that against some threshold, and in fact, the threshold will be 0, in order to decide which of the two classes it belongs to. If the inequality is if the inequality holds, it goes into class 1. If it doesn't hold, it goes into class 2. But if both of these are linear models, notice that we can rewrite this, and I'm actually going to use some vector notation here just to simplify writing it. I'm not done. This is just the first term, where that inner product W transpose X is the weighted sum that we have seen so far. And then W sub 1, 0, this is the W0 weight for class 1. And then we'll subtract off, stick a 1 there too. And here's the second weight matrix for the other class. So all I've done is now subtract the two linear functions. Well, notice that I can now rewrite this way. All I did was rearrange the terms. Since W1 and W2 are vectors, I can simply add them together. And then I also have the scalars for those two extra weights, which basically reduces to a new linear function. The point being, what this does is it justifies only one function is needed for two classes. I mean, we could have done that anyway, just looking at the geometry again, because as you can see, I mean, this is showing geometrically what's going on here, where I have two classes denoted C1 and C2, and I've drawn a line that is separating those two classes out. So at least this matches the intuition, but it's a little bit stronger than just matching intuition, because what it also shows is, yeah, I could have gone back and I could have trained those two models separately, just like I was doing in the multi-class case, and then take the resulting models and combine them, as shown here, to get a single model. All that meant was that for the two-class problem, we simplified the computation required by only having to focus on that single model. But where things get interesting is when we go back to multiple classes. So more than two classes. All right. Now, you remember what we had you do? You trained a separate model for each class. Now, there were a couple strategies that were available to you. The strategy that I proposed is sometimes referred to as one versus all, or it's also referred to as one versus rest, where the idea is that you're going to learn a separate classifier, a separate linear model for each of the classes that looks something like this, where what we're doing is we are separating, let's see, where's class one? Here's class one. We're separating class one from the combination of classes 2 and 3 by learning the single linear model. And then for class 2, we do the same thing. We're separating class 2 from the combination of class 1 and class 3 by learning this single linear model. And finally, for class 3, same thing. We're learning a single classifier separating this class from the combination of C1, C2, as shown here. Now, this is a very telling diagram in that we've got this odd space in the middle. And the question becomes, what happens if you fall in that space? Because none of the classifiers are going to classify the data there if you impose that strict inequality. And there might even be situations where let's see if we can find one on the diagram here. Sure. Look in this region right here, where if you fall there, notice we're on this side of H1, which is the class 1 model, and we're also on this side of H3, which is the class 3 model. So in that case, what it's going to do is say, oh yeah, this data point belongs in both class 1 and class 3. But we only want one decision. So we have the two extremes, where on the one hand we get no decision, and on the other extreme we get more than one. What do? Well, there are a couple strategies, again, that have been proposed. One strategy simply says, choose class I if the value coming out of that classifier is the max over all of them. And in fact, I believe that is the method that I recommended that you use. All right. Another approach is to say, well, this one versus all is losing too much information. So as an alternative, we can apply a strategy that's referred to as one versus one, or sometimes called pairwise separation. So the idea here is that you're going to learn a single linear classifier for every pair of classes. Now, that can get expensive depending on how many classes you're dealing with. So suppose we have k classes. In the one versus rest method, we only have to learn k models. In this case, however, we need k times k minus 1 over 2 models because of all of the pairwise combinations. And then what do? Well, we have choices again. One choice says, choose Ci if for all j not equal to I, Gij of x is greater than 0. In other words, we will pick the class Ci if its pairwise models always win. But that's really strict. And in fact, in general, it simply doesn't hold. So another strategy builds off of the idea that we used for the one versus all method, where we calculate for Gi the sum of the individual models that involve class I, and then choose Ci if Gi is the max. Which also, if you wanted to put that down instead of looking at the raw values and just count the number of times that G sub I is the largest, basically reduces to voting. But this is a little bit finer grained because it can also be used to break ties. All right. I need to stop there. What we will do on Wednesday is look at the perceptron and the Adeline network, which I wanted to do before we jumped into logistic regression. But before I let you go, are there any questions? Okay. Well, have a good rest of your day, and we will see you all on Wednesday.